Hello everyone, I am Shayok Kumar Dhar. Now going to discuss about a very important theorem in mathematics. It's very important for graduation in mathematics honors also. It is Bolzano Weierstrass Theorem. Okay, its statement is every bounded infinite set in R has at least one limit point. Okay, I will prove it, and I will prove it in a very simple and manner, and I will explain it beautifully. Okay. So to do this, we have to know about infimum and supremum of a set. Okay, if let A be a set. Okay, let A be a set which is bounded above. Okay, and A should be a non-empty set. It should be non-empty. It is a non-empty set which is bounded above. Okay, then supremum of A exists. Okay, fine. And what is supremum of A? Supremum of A is such that for any A belongs to A, suppose M equals to supremum of A. Okay, if M equals to supremum of A, then supremum of A has these two properties. Okay, 1 and 2. First property is for any A belongs to capital A. Okay, small a lesser equals to M. This is the first property, and second property is for any epsilon greater than 0. For any epsilon greater than 0, there exists X belongs to A such that M minus epsilon strictly less than X, and that is lesser equals to capital A. These two properties holds for supremum of A. Okay, if M is supremum of A, then these two properties always hold. And to exist supremum of a set, it should be non-empty and it should be bounded above. Okay. Now for similar manner, I can define infimum of A. To have infimum of A or infimum of a set, the set should be non-empty and that should be bounded below. Okay, that should be bounded below. Then infimum of A exists if I take small m equals to infimum of A. Okay, then for any A belongs to A, just it will reverse, that is small m lesser equals to A. Okay, and for any epsilon greater than 0, there exists X belongs to A such that small m lesser equals to X, and that is strictly less than M plus epsilon. Okay, fine. These two are the very well-known properties of infimum, and the previous two was important property of supremum. Okay, fine. Now I will move to my main portion. Okay, it is to prove this theorem. Okay, fine. Now I'm going to start it. Fine. Now look at this. I am going to the proof section. Proof. Okay. It has been said that every bounded infinite subset of R. So I have to take a bounded infinite subset of R. So let S be a bounded infinite subset of R. Okay. Okay. Very good. Now let capital M equals to supremum of S. Since it is bounded, look at this. Since it is bounded and infinite, it is bounded means it is bounded above and also bounded below. Okay, so because of it is bounded above, its supremum exists. Just because of it is bounded below also, its infimum also exists. Okay, and not only that, it is infinite. Okay, so it is non-empty. That's why its infimum and supremum both exist. Okay, to exist infimum or supremum of a set, that should be bounded below or bounded above, and that must be non-empty. Okay, fine. just because of it is bounded and infinite, so its supremum is exists. That's why let m equals to supremum of S and small m equals to infimum of S. Fine. And I am taking a set H. I am taking a set H such that X belongs to R. H is defined by X belongs to R such that X is greater than infinitely many elements of S. Okay, I have defined a set H such that it consists of those elements which are greater than infinitely many elements of S. It is like if this one is S, okay, and then H is the set if that will start from this point. Like if this point is greater than infinitely many points of S, okay, then H will start with this point and it will move forward and forward. Okay, my goal is to show that this I have to prove that this set S has at least one limit point. Okay, so I will show that this infimum of H, infimum of this set is limit point of S. That is my goal. Okay, so for that one, infimum should exist of H. So for existence of infimum, I have to check whether it is non-empty or not, and whether it is bounded below or not. If it is non-empty as well as bounded below, then this infimum of this set will exist. Okay, fine. Now look at this. That is capital M is greater than equals to small s for all small s belongs to S. Is it not? And S is an infinite set, so capital M is greater than infinitely many elements of S. Correct? That's why it implies that M belongs to H. Is it not? Correct? So which implies that H is non-empty. Now my goal is I have two goals. To show that my first goal is H is non-empty, which I have already proved, and my second goal is to show that H is bounded below. That is my two goal. Then that will imply that infimum of H exists. Okay, so I have two goals. My first goal is done. I have already showed that H is non-empty. Now I have to show that H is bounded below. Okay, fine, very good. So to show that, look at this. My H is bounded below. I am taking, let small h belongs to H. I am taking an element from H, and I can take it because H is non-empty. So I can always find an element into H. Okay, fine. Now cannot I write that this M is strictly less than H? Yes, I can write. What is the reason? Behind everything what I am writing, there is a reason, and I am explaining that. Okay, the reason is no elements less than or equal to M can exceed infinite elements of S. That is the reason. The reason is no elements less than or equal to M can exceed infinite elements of S. How can it exceed? Because M is what is M? My M is infimum of S. That means M is lesser equals to small s for all S belongs to capital S. Is it not true? So M cannot exceed infinite elements of S. Okay, and that's why just because of M can't exist infinite elements of S, and this H just because of it belongs to capital H, and the nature of capital H is the elements of H exceeds infinite elements of S. Okay, that's why this element H exceeds infinite elements of S, and this M can't exceed infinite elements of S. That's why m should be strictly less than h. Okay, fine. I hope you have understood. Okay, fine. Okay, then that implies, now what it implies? It implies that h is bounded. H is bounded below. Why? What is this? If I tell that h is bounded below, then it should be a lower bound. Now you watch that this small m is a lower bound of h, is it not? Just because this small m is a lower bound of h, because I have taken an arbitrary element from capital H, and just this small m is strictly less than that h or less than that h. Okay, that's why m is lower bound. What is the definition of lower bound? It's the definition of lower bound. Okay, so that's why m is a lower bound of h. Clear? So just because of h is bounded below, so my second goal is also fulfilled. Okay, that's why infimum of h exists. Okay, so now I can write that just because of h is non-empty and h is bounded below, infimum of h exists. Okay, now I am erasing all these things because I have proved this, and I am writing that. Now I am writing that infimum. I can write that infimum of h exists. Okay, it implies infimum of h exists. Okay, so if just because of infimum of h exists, let xi equals to infimum of h. What I will show? I will show my target or my goal. I am writing it like this. That's bullseye. Okay, that is xi is limit point of s. That's the bullseye. I haven't proved it till now. I will prove that. Okay, that's my target. Okay, now to prove this one, just look at this. Since xi is infimum of h, what is in the picture? Let this is the set S and this is the set H. H starts from here and it's going forwards to and going on and on. Okay, so and let this is infimum. Okay, this is infimum. It means this is xi. Okay, let this is my xi. This point. Clear? Okay, that's why just because of xi is infimum, let epsilon greater than 0. Okay. Then what is the property of infimum? I have written one property of infimum, that is there exists an element y belongs to H such that xi lesser equals to y strictly less than xi plus epsilon. Okay, this is the property of infimum property. Okay, now this y belongs to H. What does it mean? It means that y exceeds infinite elements of S. Infinite elements of S. So it implies now if y exceeds infinite elements of S, this point is also greater than y. So it should exist infinite elements of S if it exceeds infinite elements of S, is it not? That's why it implies that xi plus epsilon exceeds infinite elements of S. Okay, this xi plus epsilon exceeds infinite elements of S. And now look at this, xi minus epsilon. This xi minus epsilon does not belongs to H, is it not? This xi plus epsilon, suppose I have taken as epsilon this one and this one. This point is xi plus epsilon. Okay, and this is xi minus epsilon. Okay, so this xi plus epsilon, this point has exceeds infinite elements of H. Okay, and this xi minus epsilon, xi is the infimum. Mind it, this xi is the infimum of H. So xi minus epsilon should not belong to H. Okay, so that's why xi minus epsilon doesn't belong to H. Now, by the property of defining H, xi minus epsilon cannot exceed infinite elements of H S because of it. Because it doesn't belong to H. Okay, so it can't exceed infinite elements of S. Okay, so it implies xi minus epsilon can exceed at most finite elements of S. At most finite elements of S. Okay, it can't exceed infinite elements of S, so it can exceed at most finite elements of S. Okay, fine. So that's why now look at this xi plus epsilon, this xi plus epsilon point exceeds infinite elements of S, and this xi minus epsilon points exceed at most finite elements of S. Okay, that means this xi minus epsilon and xi plus epsilon, between this there are infinite elements of S. Is it not? It exceeds at most finite elements of S, and this exceeds infinite elements of S. That's why between this and this there should be infinite elements of S. Okay, so I'm writing this one, that is xi minus epsilon to xi plus epsilon contains infinite elements of S. Okay, I have wished that this xi minus epsilon and xi plus epsilon contains infinite elements of S. Now, what is this? This is a neighborhood of xi, and this is an arbitrary neighborhood of xi. Why? This is an arbitrary neighborhood of xi. What is the reason behind this? Because I have taken epsilon as arbitrary. I have taken epsilon arbitrarily greater than 0. So it means that it implies that every NBD neighborhood of xi contains infinite elements of S. Okay, every neighborhood of xi contains infinite elements of S. Is it not? Because it is a neighborhood of xi and it contains infinite elements of S, and epsilon was arbitrary. Okay, so every neighborhood of xi, it means every neighborhood of xi contains infinite elements of S. Fine. Now what does it mean? What is the definition of limit point? Limit point means if any point is limit point of any set, that means every neighborhood of that point contains infinitely many. Actually, it contains infinitely many elements of S, because any limit point in R is an omega limit point. Okay, it contains, if it is limit point, then its intersection with that set is always infinite. Okay, so every neighborhood of xi contains infinite elements of S, and that implies that xi is a limit point of S. And I am already there. I have to prove that xi is a limit point of S, and I have proved that. So I have to prove that S has a limit point, and I have proved that xi is a limit point of S. So I am true. Okay. So to watch more videos like this, do subscribe, like, share, and comment.